Dr. Keegan is a lecturer at the University of Johannesburg's Applied Mathematics and Mathematics Department. He has worked in the field of celestial mechanics and classical mechanics, classical mechanical dynamical systems. His current research interest includes the modeling and analysis of dynamical systems, specifically mathematical Bilot systems. So I'm really interested to hear what all of this is about. Dr. Keegan, over to you.
Thank you very much for that warm introduction, Lungi. So my talk today is about applying mathematics to the real world. Now in school, mathematics, you often just want to solve for variables x and y, for polynomial equations, or finding the geometric relationships between circles or triangles, or to solve pesky trigonometric problems. But we can also apply mathematics to help us solve real-world problems by analyzing and solving and constructing mathematical models. And the field of research dedicated to solving real-world problems using math is called applied mathematics. But to understand what applied mathematics is, we first need to just define what mathematics is. And that is the study of numbers, formula and related structures, what students or learners might know as algebra, shapes and the spaces in which they are contained. This is geometry. Learners should be familiar with Euclidean geometry. And something which gets introduced at university is the study of quantities and their rates of change, which is known as calculus. With that said, we can now say that applied mathematics is related but different, because we study mathematical models that represents real-world phenomena which arise in the sciences and engineering. So applied mathematics as a field uses mathematics as well as the knowledge from other disciplines like physics, computer science, engineering, economics, social science, etc., to describe and solve mathematical models. So what is a mathematical model? It is a representation of a real-world scenario or system using one or more mathematical equations to gain qualitative or quantitative understanding of this scenario or system, and also for us to try and predict future behavior of the scenario of the system. And the process of constructing a mathematical model is what we call mathematical modeling. So how do we construct a mathematical model? Well, I made this small graphical representation of the whole process, but it can be quite involved. So we'll start off with our physical problem, and then we will construct a model. And this model may or may not be solvable analytically. If it's not, we will then resort to what we call numerical modeling, where we create a numerical model, which we will then program into a computer to then try and crunch numbers for us and give us a computational solution. Now, in the process of modeling, you do introduce an element of error. And so we have to verify our models against test data to make sure that what we've constructed is an accurate representation of the physical problem, or gives us results which we expect. But talking about physical problems, there are roughly two different types of problems that arise in real-world scenarios. The first type of problem is where we are interested in the long-term behavior of the system to try and predict what is going to happen in the future, given some past or current data. And the second type of problem, second type of problem is where we want some type of optimal solution. All right. With the long-term behavior type problems, we often use differential equations to model these things. And for the problems where we want an optimal solution, we use optimization. And I'm going to discuss each one of these in turn. So the first type of problem, long-term behavior, this is what we often refer to as dynamical systems, where we consider that the equations we come up with in our mathematical model might not have a solution as what learners know in school. So rather, instead of trying to find a solution, we want to study the behavior of our unknown variables as they change with respect to a known variable over long periods of time. And we want to be able to determine whether this system of equations either display periodic or stable behavior, which is nice and predictable. That is what we're looking for. But sometimes we find that these systems display aperiodic or unstable behavior, which is completely random and chaotic, which is not something we would want if we are using our mathematical models to predict future results. And the way we talk about these systems, like I said, is by the use of differential equations, which I've given an example equation here. In this equation, our t represents an independent variable, which refers to the physical quantity of time. P represents our dependent variable, and it's dependent on t, so dependent on our time. This model is ironically for population dynamics. So the P here represents a population density. And the dp over dt term is what we call the first derivative of P. And it represents the rate of change of the population density as time changes. So in this example equation, the dependent variable P is considered to be unknown. And that's what we usually want to solve for. But we can also get some quantitative and qualitative results just from studying this differential equation. So where are these applied in everyday life? Well, the first is, like I've mentioned, in population dynamics, and these figures represents results from what we call a predator-prey system. And this, the figures represent nice periodic stable behavior. So we can tell that the populations of both the predators and prey are going to go up and down in time. So it repeats periodically. Right. Another application of population dynamics is epidemiological population dynamics, where we study the long-term behavior of epidemics, and our populations are represented in humans, say, for example, where we have susceptible, infected, or recovered populations and how these change with each other. Colleagues of mine in the department made very good use of this in during COVID times to study certain aspects about social distancing. So it's very important that we understand epidemics and how they evolve. But another application which I know a little bit more of is like mechanical systems or celestial dynamics, studying the long-term behavior of satellites or launching satellites from the Earth, getting them to go to the moon, so on and so forth. Very interesting field. I love it to bits. But let's take a quick look at our other application area called optimization. And this more arises in financial and industrial type problems, where we are concerned with determining some optimal solution to a given problem. And these problems can include, but they're not limited to, say, maximizing the revenue or profits from selling certain products or services, minimizing costs in the manufacturing of products, optimal placement, say, of wireless network nodes to maximize network coverage and minimize power consumption of these wireless network devices, optimal units of different food types in a diet to maximize nutrient intake and minimize the cost of food type purchases. This is called the diet problem. And lastly, trying to determine an optimal route a traveling salesman should travel between cities to minimize travel time and maybe maximize his revenue from selling his wares. optimization is very impactful on our daily lives, even though we don't often see it. And scenarios where this is applicable is delivery companies determining routes to minimize time for delivery. And in that same breath, to minimize, say, carbon footprint by finding optimal delivery routes. You can think that if a delivery route is not very optimal, car will use more fuel, and that will create more exhaust or greenhouse gases that get released to the atmosphere. So this is a very important problem which we want to find answers to. Sustainability and reducing our carbon footprints, reducing our energy usage. Another way this is impactful in terms of sustainability is reducing construction material costs or the usage of construction material. A good example of a problem here is what they call the cutting stock problem, where we want to minimize the wastage from different cuts in like a square timber board. And we have determined cuts that we want to make, but we have a big board out of which we want to make all of these cuts, and to try and minimize the wastage, the leftovers. Another example of an impact on our lives is in the agricultural sector, where farmers have to try and plan their crops to maximize their crop yield and profitability while reducing, say, their planting costs, routes for their farm equipment to travel, so on and so forth. All right. I can go on forever, but I was given 15 minutes to give this talk, and I see I've got about 4 minutes left. This is just a brief tip of the iceberg in terms of mathematical modeling and how we apply mathematics to real-world scenarios. There are numerous other applications and problems that are studied using mathematics and applied mathematics and the relevant other disciplines involved. So for example, the computer science or social sciences. Another example I can quickly mention is fluid dynamics. So understanding airflow over the wing of an aeroplane, or better aerodynamics with your cars to reduce drag and increase fuel efficiency, so on and so forth. So I hope I've piqued your interest for further studies in future. And I want to tell you that applied mathematics is offered as a major in mathematical sciences degrees at most universities in South Africa. It's also offered as a second major in some physics or physical sciences degrees. So please look out for that and look at universities' prospectus documents if you're interested in going down this route. And just to briefly mention career opportunities with applied mathematics, the big three, which I've seen over the years speaking to students who've done this degree and going on into careers. First and foremost is an academia or education, becoming a university lecturer or a mathematics teacher. The second one is IT or software development, programming, developing software. Even though you might not take computer science in your mathematical sciences degree, software companies still look for your problem-solving skills you develop while pursuing applied mathematics degree. And the last career opportunity is quantitative analysts. This is working for banks or financial firms and solving problems related to that. And with that, I will conclude my talk. Thank you very much for listening, and thank you very much for this opportunity to present the field of applied mathematics to the eager young minds of tomorrow.
Thank you so much, Dr. Anderson. Very interesting presentation. And I must say, when I was in high school, which is many years ago, I was very clueless on what applied mathematics was. I think it was just, that was in the time of higher grade and standard grade mathematics. So in high school, we were never really introduced to applied mathematics. So firstly, it's a privilege for some of these kids. It's really amazing that we are getting all of this information. So before I go into my question, there is a question on the chat. And one of the participants wants to know, is applied mathematics a good major for students who want to become actuaries?
I think that is dependent on the university. Different universities have different approaches to applied mathematics. I don't want to say yes or no, but what I will say, at least from UJ and what I know of the UJ curriculum, is that our applied mathematics is more geared to physics and computer science type applications. I would suggest for actuarial science, applied mathematics may be combined with statistics, because statistics is also a big part of actuarial science.
Oh, okay, great. So one last question. I think we still have time for one or two maybe. So in your opinion, so I know you did mention that if students want to do applied mathematics or mathematics, they should check out the different university perspective guides. But what I would like to know from you, from a high school student's perspective, in your opinion, being that you've been in the industry for quite a while and you've taught applied mathematics for a long time, what do you think students should essentially work towards as a good mark in high school for them to even be competitive for applied mathematics? Because, you know, now universities are extremely competitive. So what would you deem as a really good mark if you want to pursue a career in this field?
Right. So I know UJ's minimum requirements is to have a 65% in grade 12 matric, but that's the minimum. That's the minimum. I would say to a good mark for a competitive entrance to university, anywhere at least 70%, but 75 to 80 would be sort of the best. But also there's a slightly other aspect to it as well. At high school level, if students have done word problems, they have done applied mathematics. That's what I usually tell first-year students. So if you want to pursue applied mathematics and applied mathematics alone, for example, I would say make sure you are able to solve word problems and to do them well and understand all the things that go into solving a word problem, the mathematical modeling aspect of it. So I hope that has answered your question.
No, it really has.
Sorry, I see one last question here in the chat about someone asked, Tsegofatso asked, do you have to do a PGCE in order to be a lecturer? So just a quick distinction between, so if you want to become a lecturer at a university, the requirements is to go up to doctorate level, so PhD. So that's numerous postgraduate degrees. If you do an undergraduate degree and a PGCE, then that will qualify you to be a mathematics teacher at a high school. So just those distinctions for students as well.
Thank you so much. Thank you, Dr. Keegan.